Section 10.5 Inferences of two population means using paired samples. So we're talking here about what? Two populations, and from each population we're gonna withdraw a sample, and then we're gonna pair these samples. That's why called paired samples. We're gonna compare these or pair these samples and see if there is a difference between their means or not, and which will generate to the entire population. Is there a difference between the mean of the two populations or not? That's what this section is about. So to do this, we need to go through some stuff that we're going to introduce here. So let's say we have population 1 has a mean mu1, population 2 has mean 2, and the difference between the mean sub d is going to be mean 1 minus mean 2. So mean means population mean. So we introduce the mu sub d for the difference, and d should be normally distributed. D is normally distributed. So we could use the tables, especially table 4. What we have to do here is we need to test a hypothesis. We test the hypothesis. Do we reject the null hypothesis, or do we not reject null hypothesis? So let's start with this by introducing the paired, let's call paired t-test, paired t-statistic test. And what does it say? It says if we suppose that x is a variable on each of the two populations whose members can be paired together, okay, and we call the paired difference d is normally distributed as I listed earlier, then for paired samples of size n, the variable t, I'm gonna call t sub 0, that's the t statistics, is defined as d bar minus, that's the mean of all these mean differences, the mean of that, minus mu1 minus mu2 divided by the standard deviation of the differences divided by the square root of n. N is the sample size. This has a t distribution, means table 4 should be used, with degrees of freedom equals n minus 1. N minus 1 degrees of freedom. So this is the one we need. Now for the setting hypotheses, the null hypothesis is going to be always assuming mu1 equals mu2. And then for the alternative hypothesis, there are three cases. Either mu1 does not equal mu2, that's two paired test, or mu1 is bigger than mu2, that's the right one, and mu1 less than mu2, that's the left one. There are three cases. But always mu1 equals mu2. So from here, we can see that mu1 minus mu2 is 0. So this tells us that this quantity here is always going to be 0. So from there, we get that t sub 0 is d bar over sd divided by the square root of n. This is what we do with the t statistic. We need to find the t statistic so we can use, as we did in the previous sections, to help us to see if this value will fall in the critical region or the rejection region or not. And that will help us to decide if we should reject the null hypothesis or not. Now, before we go over this example here, let me just introduce right here, right below the table, the strategies. Like, how do we start with this one? So, of course, you state the hypotheses. And this works all the time in almost all these tests that we have been performing. You state the hypotheses. Alpha, the level of significance, will be given to us. It will be given to us. And what we need to do is, there are two methods here. So first thing you do is you find t sub 0. Okay, the way I showed you the formula, this over s sub d square root of n. S sub d square root of n. Then from here, there are two things we can do. Two things we can get. First one is the critical value, but that requires the given alpha. whatever alpha is given. And we go to table 4. We use degrees of freedom, of course, and -1. Then we go to table 4. And watch what we're going to do with table 4. In table 4, degrees of freedom are on this, in this column. Those are the degrees of freedom, and -1. And on the top, we have the T sub alphas. Let's say like that. So you would know what that is. It will be given. And you will be able to find this by doing n-1. Let's say it's somewhere here. And all you have to do is just go vertically this way, horizontally this way. This will be the value we're looking for. That's the critical value. And why do we find the critical value? Because then if we compare the critical value to this, if T sub 0 falls in the critical or rejection region, we reject the null hypothesis. Otherwise, we don't reject the null hypothesis. So this will tell me, it will tell me where's the critical region is. If it's a two-tailed test, it will be here and here. This would be T sub alpha, and this is negative T sub alpha. That's for two-tailed test. That's when mu1 does not equal mu2. If it's bigger than, maybe let's say here, T sub alpha, bigger than would be this one. That's when mu1 bigger than mu2. The shaded regions are the, what we call them, the critical regions or the rejection regions. Here we have a 0 in the middle, 0 and 0 here. For the other one, it could be here or anywhere, T sub alpha or negative T sub alpha. That's the critical region. That's when mu1 is less than mu2. This is the first thing. That's one method to decide if we need to reject the null hypothesis or not. Are we going to reject the null hypothesis or not? The next one is the p-value. Some students find difficulty with finding the p-value. So we're going to find the p-value. What is the p-value? It's really important to know what it is. This is a probability. It's a probability. So when we try to find what that is, the answer has to be somewhere from 0 to 1. It can't be more than 1. It can't be less than 0. And the idea, the reason we find the p-value, then we compare the p-value with alpha. So if p less than the p-value less than alpha, then we reject the null hypothesis. Otherwise, we don't reject the null hypothesis. That's why we find. Now, how do you find the p-value? It can be tricky from table 4. It can be tricky. If we are finding this, especially for two-tailed tests, two-tailed test is tricky. Now the t-table, if you look at the t-table, it gives us to the right of the t-value, to the right of the t sub alpha, the region. So the p-value, what would be the p-value here on the graph? Let's say t sub alpha here, and we have the right one, mu1 bigger than. The p-value is actually the area of this shaded region. Area is the p-value. That's what the p-value is, and this will be found from the table. We can try to find it from the table, and then how do we find that from the table? Then the p-value here is really the probability, means the area when t is bigger than t sub alpha, and we do need to find this using table 4. Now in table 4, how does it work? Of course, you need the degrees of freedom all the time, degrees of freedom from here. And as soon as you find degrees of freedom, you can draw a row like this. And then we have the t sub alphas there, it's called t sub alpha 1, t sub alpha 2, t sub alpha 3, And what we need to find is the t sub 0 that we found, the t statistic, this one that we found. So we're going to use it here, right? We're going to use it. And how do we use it? That in the table. We try to find on this row, in this highlighted row, where does that fall in? Where does the t sub 0? Well, it's most likely or very rare, like almost impossible to find it right below one of those t sub alphas. So let's say you find that that number falls somewhere here in between these two. So if you draw a vertical line or vertical column, so it falls between t sub alpha 1 and t sub alpha 2. Okay, Then assume alpha 1 here is less than alpha 2, less than alpha 3. So then what is the p-value? The p-value in this case would fall, let me write to the right side. The p-value would be the one between the alpha 1 and alpha 2. Alpha 1 and alpha 2. So we can't sometimes find exactly the value of the p-value, but we can estimate it. We can find it falls between these two numbers. And that will really tell us, it will help us to compare. Then we compare the p-value with the given level of confidence alpha, with alpha. And then see if the p-value less than or equal to alpha, we reject our hypothesis. Otherwise, we don't reject it. So that's what happens if you have it this way. Now, sometimes if you are doing, let's say, left tail test, and you get a negative value, negative t sub alpha, then how do you find the p-value here? Well, the p-value, again, is the same thing as the probability that t is less than that negative number, okay, that negative number, whatever that number is. And in this case, by symmetry, if you have negative t sub alpha, then t sub alpha would be on this side. By symmetry, the area here and the area there are exactly the same. So we can do the probability that t is bigger than that positive with that number. These two numbers are the same. Okay, then we use table 4 to find the p-value. We'll see where does it fall, between which values does it fall in. That's for this part. Now, sometimes we need to look at the case when we have two-tail tests. It's important, two-tail test, because we need to figure out the p-value for the two-tail test. So how do we do that? For two-tail test, which goes like this: t sub alpha, negative t sub alpha. So this area and this area together, not just one at a time, both alpha. So this is alpha over 2. This is alpha over 2. Each one is alpha over 2. So when we use the table 4, we can do the same thing to find the p-value. Is the probability that t is bigger than that t0 that we found, bigger than t0. And then we are going to the table and try to find what that value is. What that value is in where is it in the table, as we did before. So you get the degrees of freedom here. Let's say that's the degrees of freedom, and then look for t sub alpha 1, t sub alpha 2, t sub alpha 3. I don't know, let's say it falls in here. Let's say it falls in here between t sub alpha 2 and t sub alpha 3. I assume they are in order, this order. So then what happens is the t value that we have to be careful about it for the two-tail test. Here is not going to just be one of them. It's going to be 2. If you remember from before, we used to do 2 times that. So then the p-value would be, what would that be? Well, I don't know what that exact value is, but we do know it's going to fall between t sub alpha 2 and t sub alpha 3. Okay, that's going to be half of the p-value, So the p-value will be really 2 times that. So you need to double these values here. And I'll show an example on that in a minute. Let's look at an example now. We have a professor who measured the time in seconds required to catch a falling meter stick for 12 randomly selected students. That's the sample size, dominant hand and non-dominant hand. The professor claims that the reaction time in an individual's dominant hand is less than the reaction time in their non-dominant hand. That's the claim at the level of significance alpha equals 0.05. And this is the data that was given to us. This is the data. So these are the dominant hands for student 1, 2, 3 all the way to 12, and non-dominant hand values. So you can see you're talking about two different samples. They're coming from two different populations. Okay, and here what happened is we usually or generally we are going to graph this. We are going to do the probability dot. So the probability dot of what? Probability dot of what? Do you graph both of them or do you graph something? Well, we are going to find a probability dot in a minute. I'm going to show you for what. But because we're talking about the two sample means for dependent samples, so what we're going to do is we are going to need to set the hypotheses first, of course, and then we find the critical value, the test statistic value, which is d bar divided by s sub d over the square root of n. And how do we, to start with this one, the null hypothesis always mean 1 equals mean 2, but the professor claims that mean 1 is less than mean 2. So that's it's a left tail test. It's a left tail test. And now what we need to do in order for us to be able to use this test, we need to make sure that the data is normally, or this coming from normal distributed data or populations, let's say. To do so, we need to find the difference, which is the xi values minus the yi values. So all you have to do is just take the first 0.177, subtract 0.179. So I'm going to do it just for one of the values, and the same for the rest will be the same. That would be a negative 0.002. The next one is 0.008. The next one is negative 0.022. The next one is 0.005. Next one is negative 0.017, 0.001, negative 0.034, 0.003, negative 0.043, negative 0.012, negative 0.020, and the last one negative 0.025. We do need to sum all these di's, and we got negative 0.158 if you add all these numbers up. So now what is the mean here? The d bar, we need the d bar, is basically the sum of all the di's, divided by the sample size. So negative 0.158 divided by 12. And that would give us d bar equals negative 0.0123. Well, sorry, 132. Usually you can round to 4 decimal places. And we need to find the standard deviation for this. You can use a calculator or Excel or anything to find this. You don't have to use the whole formula to find out, but I can write the formula for you if you like to do it manually. 0.0164. The formula to do this is SD is the square root of the sum all the di squares minus the sum of di's squares over n divided by n minus 1. N is the sample size. So from here we can find t sub 0. D bar is negative 0.0132. SD is 0.0164 divided by the square root of n, which is 12. So t sub 0 is negative 2.788. That's t sub 0. Okay, that's t sub 0. That's the t statistic value. Now from here we can go in two different ways to finish solving the problem. So the first method is the critical value, and the other one the p-value. So here we need the alpha, the given alpha 0.05. By the way, before I forget, we do graph the d, the difference. And so here when I said probability dot of the difference, and when you do that, if you remember, when you do that, all the points will There will be no outlier, basically, no outlier to, to ruin the figure for us. So this verifies that the data come from a population that is approximately normal with no outliers. That's what this we call box plot or probability plot. Now back to this one. To get the critical value now, this is t sub 0, and we need the degrees of freedom, which is n minus 1, in this case 12 minus 1, 11. And we need to go to table 4 to find that out. So I did the upload table 4 here to this page. So we have 0.05. So I'm going to scroll back up. Okay, so this is table table 4, 0.05. This is 0.05. And degrees of freedom 11. This is 11. So if you go across 11, notice, and down, they overlap here. 1.7, 1.79, 1.796, 1.796. That's the critical value, 1.796. $1.796. So this is the critical value, t sub 0.05. And what we need to do from this one, this is using the critical value, not the p-value, the critical value. So that tells me if I draw a figure like this, this is 0, 1.796, and it was less, so to the left. And now we found t sub 0. T sub 0 is negative something. So the t sub 0 falls somewhere in here. That's t sub 0. So it does fall in the rejection region, right? So since t sub 0 falls in the, you can say critical or rejection region, critical / rejection region, we reject the null hypothesis. So we reject the null hypothesis. Now, so to interpret this, I like to interpret it. This means there is sufficient evidence. There is sufficient evidence to support the professor's claim. Right? There's sufficient evidence to support the professor's claim that the reaction time in the dominant hand is less than the reaction time in the non-dominant hand at the level alpha equals 0.05 level of significance. And now the second method is the p-value. Okay, we need the p-value. How do you find the p-value here? We are going to find the p-value and compare it to the alpha, the value of alpha. So how do we find the p-value here? Well, the first thing we do is we have degrees of freedom, again, 11. And the p-value, in this case, is the probability that t is less than t0, which is the probability less than t less than the value we get negative 2.788 up there on the left side. But because of the symmetry of the t distribution, the area under the t distribution to the left of this number is the same as the probability t0 bigger than 2.788 by symmetry. So we are dealing with positive numbers, so we don't bother with the negative ones. Now we are going to go to the table 4 and find this out with this degrees of freedom 11, 2.788. So we're going to scroll up to find this. Okay, so let me erase this stuff. So let me write the t value down, 2.788, and the degrees of freedom 11. This is degrees of freedom 11. So if we go across this, so we're going across, let's use just the marker itself. This one. So if we go across this degrees of freedom, what is the 2.788? You're not going to find it here, but you do find it's between 2.718 and 3 point something. So it's between this and this, t sub 0.005 and t sub 0.01, t sub 0.01. So that tells me that the p-value will fall between these two values. Okay, let me write down here. Using table 4, we see that the p-value falls between 0.005 and 0.01. And now I need to compare it, and we have alpha 0.05. So note, what do you note? Note that the p-value is less than alpha. So we reject null hypothesis. That's how we do it. That's how we do it. The other thing is, if we have, I can show an example. If we have two-tailed test, which will follow the same strategy as this one. So let's say we have a two-tailed test. Just to show you guys how to find the p-value. So let's say we have a given data from any population. Say if you want the data, I can write here, say some pair of something, and then we have population 1, something coming from population 1, population 2, and let's come up with these numbers now. 1, 2, 3, 4, 5, 6, let's go up to 7. And we have 13, 16, 13, 14, 12, 8, 17. And we have 11, 15, 10, 8, 8, 9, and 14. What we can do here, we can find the difference. Okay, so we can find the difference. We all need the difference. 13 minus 11, 2. 16 minus 15, 1. 3, 6, 4, -1, and 3. And what we can do is we can add all these di's. That gives me 2 plus 1 plus 3. That's 6, 6, 12, 14. That's 18. And then d bar that we need is the sum of all di's over n. So 18 over 7. And that gives me 2.571. That's what we have. Now for the standard deviation, if you want to do it by hand, is the square root of the sum of these square. Means you square each difference. So if you like to do it here, you can find d square, which is 4, 1 square 1, 9, 36, 16, 1, and 9. And then add all these numbers up. That gave me 76. So minus, you sum all the d's and square it divided by n over n minus 1. So this one here was 76. This one, you find the, this one we already found the sum of the d's. It's 18. So it's 18 square over n. N is 7 over 7 minus 1. Of course, calculator is needed here. Can do everything by hand. And that give me 2.225. So then I want to find t sub 0, that t statistic value, which is d bar divided by s sub d over the square root of n. This one is 2.571 over s sub d is 2.225. divided by the square root of n, which is 7. And that gave me 3.057. That's what it gave us. So this one. Now I'm going to just show you the p-value. The degrees of freedom is 7 minus 1, which is 6. And we need this one and the table. So we are going to go to table 4. Okay, we're going to go together to table 4, keeping this number in mind and the degrees of freedom, 3.057 and degrees of freedom. So let's go to table 4, back to table 4. Okay, let's erase everything we have. Okay, let's erase everything. And we had T sub 0 is 3.057. Degrees of freedom is 6. So this is 6 here. So we're going to go across this. And 3.057, what is that going to be? Is going to be between two values, this value and this value, right above the line. So it's between 2.447 and 3.143. If we move up, if we project it up, that gives me T 0.025 and T 0.01, right? Because this is 10 here. This is smaller than this. But what that happens, does that mean the p-value between this and this? No, it's 2 times those. Remember, because it's a two-tailed test. So it's going to be, if you multiply this by 2, that would give 0.020. You multiply this by 2, 0.025 times 2, that would give 0.050. Okay, so these are the p-values or the range of the p-value. So I'm going to put, I'm going to have the p-value here. The p-value falls in between 0.02 and 0.05. And let's say it is given alpha to be 10%, which is 0.10. So what do you notice here? We notice that the p-value that we have is less than the alpha. So we reject the null hypothesis. So I hope the way to find the p-value is easy now for you guys. And back to the slides, if there's anything else, just to show you that everything was covered here. So this is the formula that we started with. And then when the mu1 equals mu2, it drops down to this one. And that's what we have for the null hypotheses or the hypothesis set. This is showing you the stuff I talked about. This is the critical value approach or the classical approach, and the p-value approach, the ones that I spoke about. The next one is to talk about is the confidence interval. How do you find confidence interval? So the confidence interval, as soon as you find the first stuff that I spoke about, the confidence interval becomes very easy. So it's d bar plus or minus t sub alpha over 2 s sub d square root of n. S sub d square root of n. So that means you're going to have one of it, d bar minus t sub alpha over 2 to give you one of the bounds, maybe the lower bound, and this will give you the upper bound. S sub d divided by the square root of n over the square root of n. So if we need to try to see an example on this, maybe we can apply this to the example that we can give you some information to find this. Let's say we can use the dominant and non-dominant example. Use the dominant non-dominant example to construct 95% confidence interval estimate of the mean difference mu sub d. So what do we need to know here? We need we are given alpha. Remember, alpha is 0.05. That's the most important here. We can find alpha over 2 alpha over 2 is 0.0, just divide 0.05 by 2, and that will give us 0.025, because that's 50 here, it becomes 25. And what we need to do is, with the degrees of freedom 11, it was 11. So if you go to the table, T table, or the table 4, you will get this to be 2.201. Very easy to find, very easy to find. And then we can go back here and then substitute the values. D bar was, we found it as negative 0.0132. This one we just found it 2.201 times, as D we had it 0.0164, and the sample size was 12. And the same thing for the other one. And if you like to get the answers, I got negative 0.023 for this one, and for that one we got negative 0.0028. So this means we are 95% confident that the mean difference between the dominant hand's reaction time and the non-dominant hand's reaction time is between these two values that we just found, this value and this value. That's these values second. That's how we interpret it. Or you can say, in other words, we are 95% confident that the dominant hand has a mean reaction time that is somewhere between 0.0025 seconds and 0.023 seconds faster than the non-dominant hand. So, and one thing to note about this, it does not include the 0 here. So that supports that, you know, the claim that we have, that the reaction time of a person's dominant hand is different from the reaction time of the non-dominant hand. So in summary, what we are trying to do here, we have samples, two dependent samples from populations, from two different populations. We're trying to test the claim about the difference of their means. Someone might say they are different, some might say less than, some might say bigger than. We're going to test this. To do so, we need to state the hypotheses, then find the t-statistic value t sub 0, and then there are two approaches here. Either you go with the critical region, finding that, or the p-value. Either one is fine. And then if you go the critical region, then you see if the t0 falls in the critical region, then we reject the null hypothesis. If not, we don't reject it. If we reject it, then there is an evidence to support the claim, which is H1 or HA, which is the alternative hypothesis. There's a claim to there's a sufficient evidence to support the claim. Or in the p-value approach, if the p-value is less than or equal to alpha, then we reject the null hypothesis. Less than or equal, we reject the null hypothesis. Otherwise, we don't reject the null hypothesis. If we reject it, this means there's enough evidence to support the claim. Otherwise, there's no enough evidence. And then the other thing to know here, how to find the confidence interval. So one thing you have to do is to always find t sub alpha over 2 using table 4. As the n and d bar are always calculated from the previous part, you just have to substitute and run some calculation.